Good evening, dear students. So let us start our class on matrices in continuation of our previous classes. So today we will start with elementary operations of a matrix. So we will see that how we can perform the elementary operations and several significance of elementary operations. Now, why elementary operations are required? Elementary operations are required to, one direct implication of elementary operations is to find the inverse of a matrix. Once we are done with the elementary operations, dear students, we will see that how we can find inverse of a matrix. And then, then we'll see the exact significance of application of elementary operations. Elementary operations, and due to elementary operations, we make a transformation. Now, let us first understand what is elementary operations. Now, before I continue further, dear students, please confirm that you are able to hear my voice clearly and able to view my the screen properly. Okay, great.
Yes, sir.
Fine. Couple of
Yes, sir.
confirmation is fine. Okay. All right. Thank you very much. Now, what is elementary operations? So let's look into it. There are 6 elementary operations on a matrix. Okay. 3 due to rows and 3 due to columns. Now, as you know, dear students, I always explain things with examples because once we look into the examples, things become very simple. Let us consider a matrix A, something like this. Let us consider a matrix something like this. Let me show you the the matrix here. Now, on this matrix, okay, we can perform operations. Okay, 3 row operations and 3 column operations, and due to these operations, we can transform this matrix. Now, as I said few minutes back, why this transformation is required, that we will see during the finding the inverse of a matrix. Now, suppose I take this matrix. The first transformation what we can do is that, we can interchange any 2 rows. Okay. Suppose Ri is the ith row and Rj is the jth row. So we can interchange between Ri and Rj. That means the content in the ith row can actually be the content of the second row, and the vice versa. Content of the second row becomes the content of the, content of the jth row becomes the content of the ith row. So, for example, if we make R1 and R3 interchanged, what we are going to get, that R1, this row, the first row will become the third row, and the third row will become the first row. Means as if these 2 rows is actually getting interchanged. That is the first elementary operations. And the second elementary operations, so this is the first elementary operations. We will discuss all these things in details. But before that, what I'm going to say is that let us understand, the fundamentals. The first one is that interchange of any 2 rows. Second one is that what we can say is that any single row is multiplied with a scalar quantity. For example, let me use a different color. For example, I want to multiply the second row of this matrix. Each and every element in this second row is multiplied with a quantity called k, scalar quantity. So what is the operation? Ri, the new Ri becomes k into Ri. You see, dear students, so I give an arrow in the left hand side like this. Why? Because the new Ri means the new element in the ith row is actually the old element in the ith row multiplied with k. Each and every element is multiplied with k. So that is, K of Ri is belongs to the Ri. So that actually what we say is the new element. So this is the second operation. For example, we can give an something like that R2, the new R2 is nothing but 3 into R2, as if that each and every element of the second row of this matrix, you are multiplying with 3 and we get a new row of this new element in the second row of this matrix. That is the second operation. Now, what is the third operation, dear students? The third operation, what we can do is that, you know, that that any element, any row, okay, can be that that row, what is the previous one, and it is multiplied with a scalar quantity of the corresponding element of another row. What I wanted to mean, I can say that Ri could be, you know, Ri, that is that old Ri plus K into Rj, where K is a scalar. That means what? If I write, for example, that my new R3 is R3 minus 2 into R1, for example, if I write like this, what does it mean? It means that each element in the row 3, in the transform matrix, means after performing the elementary operations, the matrix what we are going to get in that matrix, that row 3, the third row, will be the original third row element minus 2 into corresponding elements of the first row, and then we get an transform matrix. We are going to now work on these 3 in details. Now, as I said in the beginning, dear students, there are 6 elementary operations. Whatever you see, these 3, similar 3 is there for column. That means what? If I tell you about the column operations, it looks like something like this. Okay, the first operation will be something like Ci is actually interchanged with Cj. Second one is that new Ci becomes K into Ci. I hope you understood it. And third one is that new Ci becomes old Ci plus K into Cj. So what about the 3 row operations? Similar 3 operations for the column. So this is what is known as the elementary operations or transformations. Now, how we can proceed with this? Let's look into it. There are 6 elementary operations or transformations on a matrix. 3 due to rows and 3 due to columns. There are 6 elementary operations on a matrix, 3 due to rows and 3 due to columns. What are those? That we are going to learn now. The first one is that the interchange of any 2 rows or columns. Okay. So here I am going to show you, dear students. The first one, as you see, is that the interchange of any 2 rows or columns. For example, if you look into this particular one, as you see in front of your screen, that the symbolical notation is that Ri is actually interchanged with Rj or Ci is interchanged with Cj. So for example, if our original matrix is this, as you see, dear students, and we make a interchange with R2, what you see in the original matrix, whatever the first row is actually become the second row, the element of the second row, because we are interchanging R1 and R2, right? And whatever the, if I give a different color, whatever the second row of the original matrix, it becomes the first row of the transform matrix. So that means what? This second row becomes the first row of the original matrix, and this first row, becomes the second row of the transform matrix. So what is this matrix? Whatever we get after this operation, that is called a transform matrix. left hand side whatever you see, that is called the original matrix, and what we get after that elementary operation, we get a transformed matrix. Now dear students, these two matrices are not equal, by the way, they are transformed. Why they are not equal? Because their corresponding elements are not equal. As you know, the equality of two matrices, when the corresponding elements are equal, then we say the two matrices are equal. But here it is not. What we get here is that, dear students, is that we get a transform matrix. So this is the first elementary operation. Now let's look into the second elementary operation. Second elementary operation is that, the multiplication of the element of any row or column by a non-zero number. Okay, so what is the symbolic notation? Let me first tell you the symbolic notation, followed by I will give an example as well. So let me first show you the note here. So what you see, dear students, is that the multiplication of the elements of any row or column by a non-zero number. What is the symbolic notation? Symbolic notation is something like Ri. As you see, Ri is actually new Ri becomes the k into Ri. What it says, as it mentioned here, multiplication of each element of the ith row by non-zero number k. Or when we say Cj is equal, Cj, new Cj is actually L into Cj. That is multiplication of each element of the jth column by non-zero number L. So let's take an example and see it, how it looks like. So if we take an example, so it looks like something like, dear students, for example, we take a matrix B and we are going to perform this, operation in this matrix. So let's see how we are going to do it. Okay. For example, dear students, if you see that, applying, let's take that matrix, B is equal to, it is a 2 by 3 matrix. It has 2 rows and 3 columns. The first row is 1, 2, 1. Second row is -1, √3, 1. Now, what is the elementary operation we are doing? We are doing C3 is actually C3, new C3 means in the transform matrix, the third column will be the third column of the original matrix multiplied with 5. What is the third column of the original matrix? This is 1. What is the content? 1, 1. Now, what we are going to do? We are going to make multiply with 5. Okay. What we are going to do is that we are going to multiply it with 5. And what we are going to get, let's see. So this is the third column of the original matrix. We are multiplying with 5. If we multiply with 5, that means each and every element of the third column of the original matrix is multiplied with 5. And what we get? We get the new third column. And this is the transform matrix, dear students. So this is the second elementary operations. I hope you understood. Now, the third elementary operations, which is actually a combination of the two elementary operations we learned now, that is the addition of the element of any row or column, the corresponding elements of any other row or column multiplied by any non-zero number. Let me explain you. Rather than saying all these statements, it is important to first understand how it actually, what is actually it means. So, let me first, explain you the example. Let us consider the matrix C. Dear students, you see the, if you look into the matrix C, it is a 2 by 2 matrix where the first row is 1, 2 and second row is 2, -1. Now, what are the elementary operations we are doing? We are doing R2, the new R2 is R2 minus 2R1. What does it mean? In the transformed matrix, the second row will be the original second row minus 2 times the corresponding element of the first row. That means what? If you look into the second, new second row, first row will remain the same. That is the new second row. What is that? It is the original second row, that is 2 minus 1, whatever you see, minus 2 into the corresponding elements of the first row. So that's why if you see that 2 minus 2 into 1, why 2 into minus 2 into 1? Because 2 is the original one, that is the 2, what we are getting. And minus 2 is what? Minus 2 is that k, that is the constant with which we multiplied, and corresponding element of the element 1. So this 1, what you see, this one, this one is actually coming here. Similarly, if you look into, if I use a different color, dear students, so then you will get this -1 -2 into 2. How you get? What is -1? -1 is this one, as it is -1. And then -2, because it is each and corresponding elements is multiplied with -2, and corresponding elements is 2. What is 2? This 2 is that corresponding element in the first row, that is this element. So from here we get this one. So after this operation, what we get? The first row remains the same. The first row remains the same is 1, 2. And the second row, second row, what we get is that 2 minus 2 into 1, that is 2 minus 2 is 0. And -1 minus 2 into 2 is -5. So what we get is the 0 minus 5. Now the point is that this is the transform matrix after this, third elementary operations. So this is all about the elementary operations. Now, as I said, dear students, in the beginning of the discussion, why these elementary operations are important? Elementary operations are important immediately to know is that to find the inverse of a matrix. Hence, we should start understanding what is meant by inverse of a matrix. What is that? Okay. Now, before going to discuss about the inverse of a matrix, let us first understand that what is invertible matrix? A matrix for which we can find the inverse, it's called invertible matrix. But under what condition we can do this thing? Okay, that we are going to learn first. So, dear students, so our next point of discussion is the invertible matrix. Okay, let me first explain you with fundamental example. Suppose a matrix is given to us is something like this. A matrix is given to us, A is something like this, 2, 1, 5, 7, for example. Now, corresponding to this matrix, we need to find another matrix B such that if we multiply A into B, we should get an identity matrix. Identity matrix means what, dear students? 1, 0, 0, 1. If you recall, in our first class of matrices, if you want to recheck, you can go through the corresponding lecture which is available in YouTube. So what is the task? Task is that we have a matrix 2, 1, 5, 7, and then we need to find another matrix. Let me write it in a different color. We need to find a matrix so that the resultant matrix, what we are going to get, that becomes a identity matrix. That is identity matrix of order 2, 1, 0, 0, 1. So what, dear students, you are learning is that if we have the matrix, this is the matrix given to us. This is the matrix which is there I wrote in the blue color. Suppose I write here A, B, C, D. This is called the inverse of this matrix, of the left-hand matrix. Why? Because if we multiply these two matrices in the left-hand side, what I'm getting in the right-hand side is a identity matrix of the same order of the matrix. So what we see here, dear students, so this matrix and this matrix is called the inverse of each other. That is called inverse. Got it? So if you look into the matrix 2, 1, 5, 7, corresponding to the matrix 2, 1, 5, 7, if we get another matrix whose elements are A, B, C, D, then what we are going to get? We are going to get a matrix whose elements are 1, 0, 0, 1. And this is called the fundamental of inverse. Then, if we define this matrix, dear students, as A, and corresponding to this A, if we get another matrix B, let me write in the same color B. And so that the resultant matrix is become an identity matrix, then the matrix B is known as the inverse of A and vice versa. That means what? A is known as the inverse of B. So what we say? We say is that if AB is equal to I, that implies B is the inverse of A and vice versa. That means the opposite statement is also true. That means A is the inverse of B. Generally, inverse is denoted by A inverse. That means we can write B is equal to A inverse. That is the way to write. So what we get? We get A into A inverse is equal to an identity matrix. Correct, my dear students? We get A into A inverse is an identity matrix. Sorry. So what we are going to learn now? We will learn to learn that how to find inverse. Can we find inverse of any matrix? All these things we'll learn. But before going to learn all these things, I just explain you what is inverse. What is the fundamentals behind inverse? Now, as we understood what is the fundamentals of the inverse, then we are going to learn about its definition and its different, conditions, when the inverse can exist. The first one, dear students, what I can say is that, as whatever I said in the last few minutes is actually, it is given in the written form here. Okay, so let me first bring it and then I will read it out, So what it says, dear students, let A be a square matrix of order M, and there exists another matrix B of the same order such that AB is equal to BA is equal to I, where I is the identity matrix of the same order M. Then the matrix B is called the inverse of the matrix A and is denoted by A inverse. Correct? So I think this is what I said by means of an example. But one new term, actually, what you see, not new term, by the way, it is a condition you can say, let A be a square matrix. That means what? That means here the matrix spelling is wrong. It should be matrix. So what it says, dear students? It says that matrix for whose inverse we are going to find has to be a square matrix. That means the number of rows and number of columns has to be same. Okay, then only we can find the inverse of such matrices. Okay, if the number of rows and number of columns are not equal for a matrix, it is impossible to find the inverse of such matrices. Okay, but we'll see, is it the only condition the matrix has to be the square matrix in order to have inverse? Okay, no, there is one more condition that also you will learn as time goes by. What is the second point, dear students? If the inverse exists of a square matrix A, then the matrix is said to be invertible. That means we can find the inverse of that matrix, hence it is known as it is an invertible matrix. Correct, dear students? Okay, now the next point what we are going to discuss is that a square matrix A is said to be invertible if and only if the value of the determinant of the matrix A is non-zero. That is, the matrix is non-singular. When the corresponding value of the determinant of a matrix is non-zero, then it is known as a non-singular matrix. Otherwise, it is known as a singular matrix. Let me explain you these steps, in little details. Okay. So what is meant by that? Let me explain you. This is a very important point. And some one of you, if you are not able to recall how to find the, the determinant of a matrix, I can also say you. Let us consider the matrix with which I started giving you the example. As you see the, matrix A is here, dear students, is that 2, 1, 5, 7. Then what is the determinant of this matrix, dear students? determinant of this matrix is that those who are not able to recall how to find the determinant, they can also follow my other video lectures on determinants, and there it is explained in details. So first we multiply 2 and 7. So what is that? It is 2 into 7, then minus 1 into 5. That is the other two elements, 1 into 5. So what is that? What we get? So this implies determinant of A, what we are getting is that 14 minus 5. That implies what we get, dear students, that determinant of A is equal to 9. Sorry. Now, as we find the determinant of the matrix A is 9, which is not equal to 0, we can say yes, the inverse of this matrix is possible. So, dear students, we learn two conditions has to be followed, has to be true in order to have a matrix, in order to have the matrix invertible. What are the two conditions? The first condition is that the matrix has to be a square matrix, and the second condition is that the corresponding value of the determinant of that matrix has to be a non-zero. That means it cannot be 0. So if a matrix is a square matrix, but the value of the determinant of that square matrix is 0, then the matrix doesn't have inverse. And if the matrix is not a square matrix, then forget about finding the determinant of this thing. You cannot find. You can only find the determinant of a matrix which is a square matrix. So if the matrix sorry, if the matrix is not a square matrix, forget about it. It cannot have inverse. Second thing is that if the matrix is a square matrix, then go for the second condition check, that is whether the determinant of that matrix is 0 or not. If the determinant of the matrix is 0, then you can say the matrix is not invertible, that its inverse doesn't exist. But if the value of the determinant of the matrix is non-zero, you can say yes, the inverse of that matrix exists. Now, dear students, what I'm going to discuss the next point. The next point is that if the matrix is not a square matrix, then its inverse does not exist, as I said. Now, let me show it to you here in a written form, so that you can, once I send you the class notes, you can you can all follow this thing along with the video lectures, because the recorded session will be available to you, dear students. Now, the next point, dear students, is that if the matrix B is the inverse of the matrix A, then A is also called the inverse of the matrix B. I think I explained you during the when I gave you the example. So, dear students, so what we get here is that something like this, that if the matrix B is the inverse of the matrix A, then A is also called the inverse of B. And that is what is actually mentioned here in my earlier statement, dear students. If you look into it, if B is the inverse of A and vice versa, that means A is also known as the inverse of B. Now, the second point is that, it's not second point, the next point is that inverse of a matrix, if exists, is unique. That means what? It is not possible to find more than one inverse of a matrix. That means what? If I have a square matrix whose determinant is not equal to 0, then the matrix is invertible. That means we can find the inverse of that matrix. Now, it is not possible to find more than one inverse of the matrix. So, hence it is informed. Inverse of a matrix, if exist, is unique. And the last point is also very, very important point. And this point is just like the property what we learned during the transpose of a matrix. What is that? It says that if both the square matrices A and B are of the same order and both are invertible, then we can say that A into B inverse is equal to B inverse into A inverse. So what I say is that A into B inverse is equal to, first you do the B inverse, and that matrix, that is B inverse, is multiplied with A inverse. If you recall, dear students, the transpose of a matrix, during that discussion, we also learned that A into B transpose is equal to B transpose into A transpose. It is, it is the same order we can use to perform the multiplication when we are finding the inverse of a product of two matrices. So in other words, what we can say in English statement, the inverse of product of two matrices is equal to the product of their inverse taken in the reverse order. And that is not true for the two matrices. You can go with three matrices, four matrices, like that. What does it mean? It means is that A into B into C inverse is equal to C inverse into B inverse into A inverse. Okay, dear students, I hope you got a fair amount of idea about that invertible matrices, under what is known as the inverse of a matrix, what are the conditions has to be satisfied, and the relevant points. Now let us find that which is the core of our discussion, that is how to find the inverse. How we can find the inverse of a matrix using elementary operations. There are multiple ways to find the inverse of a matrix. So today we are going to learn using the elementary operations. And dear students, we will find that we can find the inverse of a matrix in a different way, in leveraging the concept of adjoint of a matrix. Okay, so that we will see later. Because in this group, I have not started discussing with the determinant. So you can either follow my other video lectures in determinants, which are available in YouTube, or you can wait for some weeks, and we'll discuss here also in this group. So, dear students, the next point what we are going to discuss is the inverse of a matrix. How to find the inverse of a matrix, that is the point of our discussion now. Let's see that how we can find the inverse of a matrix. So what we know, dear students, so far, for a square matrix A, we can find its inverse if exist by means of the elementary row operations or elementary column operations. First, I will tell you what are those operations, and then I will explain you that with real examples, how to perform that. So what is the fundamental point, dear students? Fundamental point, what I wanted to mean is that, first let me write it down and then let me explain. For a square matrix A, we can find its inverse if exist. With this word or with this statement, if exist, what does it mean? It means is that this statement if exist, as if it actually implying the determinant of the matrix A is not equal to 0. And the matrix is a square matrix is already informed. So both the conditions satisfied. As we know, as we learned a few minutes back, the inverse of a matrix is possible if it satisfies two conditions. First condition is that it has to be a square matrix. And second condition, the determinant of that corresponding matrix has to be not equal to 0. So now, as both the conditions are, we assume are satisfied, then let's find what is the elementary row operations or elementary column operations. So here are the steps, and we are going to execute these steps by means of real examples. Okay. So following are the steps to be followed to find the inverse of a square matrix by means of elementary row operations. Let me first show you the notes, and then I will explain you in details, as I said, by means of an example. Okay. Following are the steps to be found. Following are the steps, sorry, I'm clearing my throat quite frequently, never mind. Following are the steps to find the inverse, if exist, of a square matrix A by means of elementary row operations. The first one is that express A is equal to I into A. Dear students, if you have a matrix A, and if you multiply that matrix with an identity matrix of the same order, you will get the same matrix. You can try, you will get this thing. Then, second point is very important. It is an English statement. I am reading it out. After that, I'll execute it, as I said. Apply a sequence of row operations on this above equation. Please note that each row operations will be applicable to the matrix A in the left-hand side, which is here. Okay. Of the above equation, left-hand side, A of the left-hand side, each, let me read out once more. Please note that each row operation will be applicable to the matrix A in the left-hand side, as I marked by the arrow, in the left-hand side of the above equation, and to the identity matrix I in the right-hand side of the above equation. That means this I. So we know what are the elementary operations, row operations. So if we apply one elementary row operation on the matrix A in the left-hand side, we should perform the same elementary row operations on the matrix I. And we should not touch the matrix A in the right-hand side. So that is why I said this statement. The matrix A in the right-hand side on the above equation will remain unchanged. So I repeat once more, dear students. We have this equation. Let me write it here. Let me draw it in a different color. So we have this equation now. A is equal to I into A. So what this steps, second step is mentioning is that if you perform a row operation A, if you perform a row operation on the left-hand side matrix of A, perform the same row operation on the identity matrix. But do not change anything on the matrix A in the right-hand side. That will remain the same as it is. That means what? After the first row operation, you will see the matrix A in the left-hand side will get transformed. The identity matrix will get transformed, but the other matrix A in the right-hand side will remain the same. Okay. Then you ask, you may have this question, sir, what row operations we are going to do? I know there are 3 row operations. What row operations I want to do? I can tell you is that your target should be to perform that row operations so that you can make this matrix A in the left-hand side to an identity matrix. And as a sequence of those row operations, that identity matrix I will get transformed to another matrix B, and you will get the right-hand side matrix A remains the same. So what we get? I is equal to B into A. What is I is equal to B into A tells you? It tells that the matrix B is the inverse of A, isn't it, dear students? Now, in all these steps, I draw an arrow here now. So here it will be a series of row operations. Series of row operations, plural number. Series of, I can write it, series of row operations. That means you can perform, multiple row operations. And what is your target? Your target, I repeat, dear students, your target is to transform that matrix A in the left-hand side to an identity matrix. As a result, what will get actually, left hand side you will get I, right hand side there are two matrices initially, one is I and another one is A. I will get transformed to a matrix B because we are performing the same row operations as we performed in the matrix A in the left hand side, whereas the matrix A in the right hand side will remain unchanged. Then what will get, dear students? Then as a result of these row operations, we will get the original matrix A equal to IA transformed to I is equal to BA as I wrote it here. Initially we had A equal to IA, but what we get? I equal to BA. Hence, the matrix B is the inverse of the given matrix A. Now, let us understand with an example. If we understand this thing with an example, things will be absolutely clear. Okay, so let us take an example and go ahead with this example. Okay, let me take an example first. Give me a minute. Let me choose a suitable example. Okay, suppose we need to find we need to find the inverse of this matrix. So obtain the inverse of the following matrix using elementary operations. So this is the example what we are going to perform. Obtain the inverse of the following matrix So what is the matrix we have, dear students? A is equal to, row wise I am reading it out, dear students, 0, 1, 2. That is the row wise reading. 0, 1, 2, then 1, 2, 3, then 3, 1, 1. What we are going to do? We are going to find the inverse of this matrix. That means in simple terms, what does it mean? It means that in simple terms is that for this matrix A, we are going to find another matrix B such that if we make A into B, I should get an identity matrix. So what we are going to do? As we just learned the steps of that elementary operations, so we should write that, we should write A is equal to I into A. A is equal to I into A. So that means what, dear students? That means this implies 0, 1, 2, 1, 2, 3, 3, 1, 1. This is equal to identity matrix of the order 3, that is 1, 0, 0, 0, 1, 0, 0, 0, 1, and then the matrix A. What is that? In fact, as we have learned that we are not going to change anything on that matrix A in the right hand side, let us keep as it is as A. Now what we are going to do, dear students? We are going to perform row operations, elementary operations. Let's take row operations. I have not discussed about that elementary column operations. It is similar to row operations. So we will perform these operations. So what we are going to achieve, let me tell you the end result. We are going to perform the series of row operations, long series, I am writing it here. Series of row operations, series of operations, so I am writing it here. Series of row operations. And what will be our target? What kind of row operations we are going to achieve? We are going to perform those row operations which will help me to find, which will help me to transform the left-hand side matrix A to an identity matrix. That means, finally, after this series of row operations, I will land up the left-hand side matrix to be transformed to 1 0 0 0 1 0 0 0 1. And right-hand side, as we perform the same operations, same series of row operations, we do not know what we are going to get. We will see what we are going to get an A. Suppose I am writing in a different color, I will get it here A, B, C, D, E, F, G, H, I, for example. Our target is to, then what we'll get is that A, B, C, D, E, F, G, H, I, that matrix is the inverse of the matrix A. So dear students, before performing these operations, I'm just telling you that your target should be to perform those row operations which will help you to transform that matrix A in the left-hand side to an identity matrix as you see it here. That should be our target. So, as if I am just saying, begin with the end in mind. We know what we are going to achieve. That we need to first fix. Now we are going to start those operations. So, what I am going to do it now, I am just removing all these things so that we can start. Because I just said that we need to start with the end in mind. So that I just said that what we are going to, achieve. Now let me do these things. So first operations, what you can think of. And dear students, the operations what I am going to perform, it may not be the unique. You can perform in different ways also. But target should be same. Your objective should be same. Okay, what is the objective? Left-hand side matrix should be an identity matrix. That's it. So what I am thinking, students, is that I am interchanging the row 1 and row 2. So this is my operations. So row 1 and row 2. So I can write it here in the, what is the operations I am doing. Row 1 and row 2 are getting interchanged. If I interchange row 1 and row 2, what we are going to get in the left-hand side? It will be 1, 2, 3, 0, 1, 2. You see, the row 1 of the original matrix is now becomes the row 2 of the transform matrix, and row 2 of the original matrix becomes the row 1 of the transform matrix. Row 3 remains same, that is 3, 1, 1. And the same operations we are going to perform in the identity matrix in the right hand side. That means it will become 0, 1, 0, 1, 0, 0, and 0, 0, 1, and then A. That is the first operation we have done. In fact, what I can do is that I can write, I can shift that writing to a little bit in the left hand side. Let me see whether I can do it or not. No, I'm not able to do it. Okay. So let me remove it and let me write it down. So what I'm going to write it here, dear students, is that, or I can do one thing. Let me write in a different color so that you can understand what is the operation we are doing. R1 and R2 are interchanged. Now the second step what we are going to do, dear students, what comes to my mind is that I'm going to write R3 as R3 minus 3R1. So in the next step, what I'm going to do, that R3, the new R3 become old R3 minus 3 into R1. And as a result of this elementary operation, what we are going to get? What we are going to get in the left-hand side, dear students, left-hand side, if you do this calculation, that R3, R1 and R2 remain same. So we can just write 1, 2, 3, 0, 1, 2. Only R3 will be R3 minus 3R1. That means 3, the new element 3 should be 3 minus 3 into 1. That becomes 3 minus 3 into 1 is 0. Then 1 minus 3 into 2. that is minus 5, and 1 minus 3 into 3, that is minus 8. Correct, my dear students? So that is the new row 3. Same operation will perform in that identity. It is no longer an identity matrix. It is already transformed by means of one step. So first two row will remain the same, 0, 1, 0, 1, 0, 0. Then what we are going to get, dear students? You will see, you will get 0, minus 3, and 1. Because the first element in the third row of the transform matrix will remain same, because 0 minus 3 into 0 is 0. Now, and similarly, dear students, what you can say is that, what we get is that, the third one, that again, the element 1, what we get is that, which is in the junction of the third row and third column, is actually we get as a 1 minus 3 into 0, that is 1. So this is the second operation we performed. Now what comes to what is the next operation we can think of? The next operation, dear students, what I can think of is something like this, is that I am going to do R1 is R1 minus 2 R2. So what I am going to do? I am going to do that R1, that new R1 become R1 minus 2 into R2. So what we are going to achieve here, dear students? So what we are going to achieve here is something like this. R1 is become R1 minus 2 R2. So with this transformation, what we are going to get, in the first row will transform to 1, 0, minus 1. And second and third row will remain same. That is 0, 1, 2, 0, minus 5, 8. This is equal to what we are going to get, dear students, in the one thing I should write A here. Yeah, in the right hand side, what we are going to get is that minus 2, 1, 0, minus 2, 1, 0, and the other two rows remain same. That is, it becomes 1, 0, 0, and 0, minus 3, 1. And that matrix A as it unchanged. What is the next operation you can think, dear student, is that I am going to make the new R3 is equal to R3 plus 5 into R2. So what I'm going to get here, dear students? So let me write the operations. You may ask that, sir, what leads you to think this kind of operations? Because my target is what? My target is to transform the left-hand side matrix to an identity matrix. And that is actually helping me to understand what row operations can leads me to that result. And now I'm thinking about the operation is that R3 is R3 plus 5 R2. So let me write it down first. What is that? R3, new R3 is that R3 plus 5 into R2. So if we perform this, what we see, dear students, left hand side, what we are going to get? 1, 0, 1, because row 1 and row 2 will remain the same. 1, 0, minus 1, 0, 1, 2, correct? But interestingly, this is already 0. Minus 5 will now transform to 0, and 8 is now become 2. So that is equal to what? Same operation will perform in this in the left matrix in the right hand side. Right hand side there are two matrices. The left matrix will perform. So what we are going to get? First two rows remain the same. Minus 2, 1, 0, 1, 0, 0. And then what we are going to get, dear students? 5, minus 3, 1. And then we get a After that, what we are going to do, dear students, is that I'm going to divide each element of the row 3 by 1 by 2. That means I'm going to multiply 1 by 2 to the each element of the third row. So what is the operation we are going to get? Operations we are going to get here is that R3 is 1 by 2 into R3. So let's find it out what we are going to get here. The first two rows remain the same, 1 0 minus 1, 0 1 2, 0 0 1. That is equal to, we perform the same thing, minus 2 1 0, minus 2 1 0, 1 0 0, and 5 by 2, then minus 3 by 2, and 1 by 2. Okay, let me do one thing. Let me write this matrix in a little bigger manner. Yes. Okay. Now I would like to take little, go back to few of the previous steps, and you see that how we have achieved. If you look into, dear students, that if you look into the left hand side matrix, we are slowly brought down to an identity matrix. If you see, if I use a different color pen, if you see from here what we original matrix, after that we come to this one, after that from here to this one, from here to this one. In all these steps, you see that we are as if we are in the right track of getting that left hand side matrix as an identity matrix, and we have achieved, partially achieved, not completely. Our task will continue. At least the third row, you see it is a 0 0 1, which is actually the third row of an identity matrix, isn't it, dear students? So now let us continue. What is the next step we can think of? Dear students, the next step what I can think of is that I am going to make the R1 as R1 plus R3. That means what? My new R1 should be R1 plus R3. So let me write the operation first. R1 is R1 plus R3. And if we do this operation, dear students, so what we are going to get it? This implies R1 is going to change. So 1 0 minus 1 will now get 1 0 minus 1 plus 1 is 0. The other two rows, that is second and third row, will remain the same, 0 1 2 and 0 0 1. So dear students, if you see in the left hand side, the first and third row, already we achieved like an identity matrix, like the first and third row of an identity matrix of order 3. So what we get in the right hand side, dear students? We get 1 by 2, then minus 1 by 2, then what we get? 1 by 2, then what we get? 1 0 0. Rest two rows will remain same, 1 0 0, then 5 by 2, minus 3 by 2, and 1 by 2. Okay. Now this we have achieved. So we are only left with the second row in the left hand side matrix, dear students. And I think you can also agree to me. What I'm going to do now? I am going to do the new R2 will become R2 minus 2R3. So what we are going to do? Let me write the operation first. So if I write the operation, dear students, show that the new R3, sorry, new R2 becomes R2 minus 2 into R3. If we perform this operation, dear students, what we are going to get? that first row and third row will remain the same. So I can write 1 0 0 0 0 1. First I already wrote that first and third row. Second row will becomes now 0 1 0. And in the right hand side, what you will get, dear students? You will get 1 by 2 minus 1 by 2 1 by 2, 1 by 2 minus 1 by 2 1 by 2. Then you will get minus 4 3 minus 1, minus 4 3 minus 1, and 5 by 2 minus 3 by 2 and 1 by 2. Complete this and we write the matrix A. We are done. We are done, dear students. So what we get in the left hand side matrix? Left hand side matrix is I. Right hand side matrix is 1 by 2 minus 1 by 2, 1 by 2 minus 4, 3 minus 1, then 5 by 2 minus 3 by 2, 1 by 2. Let me write the left hand bracket little lengthier. This into the original matrix A. So what we can conclude? We can conclude this matrix, what you see, this matrix is the inverse of A. Isn't it, dear students? This is the inverse of A. So what we get? We can call this matrix as the inverse of A. So what we can say? We can say A inverse is equal to this matrix 1 by 2 minus 1 by 2, 1 by 2, minus 4, 3, minus 1, 5 by 2, minus 3 by 2, 1 by 2, and done. So, dear students, with this, all these steps by means of these elementary operations, in fact elementary row operations, we are able to find the inverse of that matrix. Now, dear students, I only explained about the elementary row operations. In the similar fashion, you can perform the elementary column operations as well. What are those? Let me explain you that what are the elementary column operations. Okay. So the elementary column operations, dear students, is something like this. Just exactly, like the row operations. Only thing is that just replace the word row by column, and that's it. Exactly the same three operations, dear students. So let me read it out, dear students. Following are the steps to find the inverse, if exist, of a square matrix A by means of elementary column operations. First is that express A is equal to A into I. Then the second step, dear students, is that apply a sequence of column operations on the above equation. What is the equation? A is equal to A into I. Please note that each column operations will be applicable to the matrix A in the left hand side of the above equation and to the identity matrix I in the right hand side of the above equation. The matrix A in the right hand side of the above equation will remain unchanged. Done. Third step is that as a result of all these column operations, we will get the original equation A equal to A into I is transformed to I is equal to A into B. Here the matrix B is the inverse of the given matrix A. In fact, this should be a plural term, column operations. Same thing. What I recommend, dear students, you stick to either column row operations or a column operations. For example, my preference is the row operations. Okay, and not only that, one more thing. If you see the way I perform all these operations, which I wrote in the blue colored, it doesn't mean that that is the only set of row operations. You can do it your own way. You can choose your own row operations, series of row operations, but target will remain the same. Target will be that whatever the matrix I have in the left hand side, I will bring it down to a identity matrix by means of transformation using those row operations. That should be the target. So that doesn't mean the set of row operations I have performed is a unique or optimized. You can find it, with lesser row operations also, hopefully. In fact, you can do it after the class, and if you get it, do share with me so that we can discuss. So with all this, we are done with the to find the inverse of a matrix. Now, next point what I'm going to discuss, dear students, is called the orthogonal matrices. Okay, so that will be the last topic for today's class, and here it is, dear students. So I'm going to tell you in the next slide. So what is orthogonal matrix, dear students? A square matrix A is said to be orthogonal if A transpose into A is equal to I. Simple thing. That means what? Let me write it down, and then we will discuss further. A square matrix A is said to be orthogonal matrix if A transpose into A is equal to I. What does it mean? That means whatever the matrix is given to you, you make a transpose of that, then the transpose matrix and the original matrix you multiply, and as a result of that, if you get the resultant matrix is an identity matrix of the same order of that of A, obviously we can say that A is an orthogonal matrix. Now we will understand the properties of orthogonal matrices. I just want to touch base on it. Later we will discuss in details with some representative examples. So here are the 6 properties of orthogonal matrices, and in fact I can recommend you that you can always experiment after the class, because you all know about the different matrix operations by now. The first one is that orthogonal matrices are non-singular. Okay, you can experiment it. Unit matrices are always orthogonal. Okay. Third one is that the value of the determinant of an orthogonal matrix is either 1 or -1. Very important message, dear students. Okay, this information, particularly the point 3, is actually being applied to solve many of the problems I have seen. That means what we can say is that from here we can say if A transpose into A is equal to I, you can say either mod A is equal to 1 or -1. The fourth point is that the product of 2 orthogonal matrices is orthogonal. Okay. If you have, that means what? If you have 2 orthogonal matrices, that means A and B, then their product means what? A into B. That should also be orthogonal. That means what? A into B transpose into A into B should be also I. So if I discuss this point, what does it mean? It means is that if you get 2 such matrices where if A transpose into A is equal to I and B transpose into B is equal to I, what does it imply, dear students? Then their product is also orthogonal matrix. That means A into B transpose, into A into B, that is also I. And you know, dear students, you can achieve this thing, you can prove this thing using the properties of transpose of a matrix and using the, associative law. The transpose of an orthogonal matrix is orthogonal. That is quite true. Okay? Because if A is an orthogonal matrix, then A transpose also has to be orthogonal. Because you know the transpose of a transpose is the original matrix. Correct, no? And the sixth one is that the inverse of an orthogonal matrix is orthogonal. So these are the properties of the orthogonal matrices. Later, when we'll solve some relevant problems, we'll discuss more on this. So with this, dear students, I'd like to conclude the class for today. But before we complete, I strongly recommend you, dear students, please log on to www.KonarClasses.com and look for video lectures, appear for different tests like, I can say you, the first such test is DPP, that is known as Daily Practice Problems. Then it is PTs, it is known as Practice Tests. Then you can appear for UTs, that is called Unit Tests. Then you can appear for MDTs, that is known as the Module Tests. Then you can appear for MTs, that is known as the Mock Tests. All these tests have been designed very well researched with our esteemed faculty members, and solving all these things will help you to achieve a great result that I can almost assure you that I'm pretty confident about. The video lectures will help you to have a good understanding. This will help you to have a good understanding of the topic. Okay? And appearing these tests will help you to, will help you in your board examinations, in your board examinations, dear students. And entrance examinations. So dear students, for any assistance, for any further assistance, you can always reach out to, always you can reach out to us in the, following numbers. What I'm going to write it here, dear students, is that our email ID is that contact@KonarClasses.com and WhatsApp me at 80950100670. So with this, sorry, it got, let me write it down once more. Let me write it in a different color. So our email ID is contact@KonarClasses.com and WhatsApp is WhatsApp to 8095010670. So with this, I would like to conclude the class for today, dear students, and we will have our next class on Monday, in which we will discuss a great topic related to the characteristic equation, and we'll proceed further. Thank you very much. Good day to you. Bye.
Thank you, sir.
Thank you very much.